Okay, this is going to be part 2 of the homework 12. Chapter 12? The homework 12 problem set. And this problem, we're going to start with problem number 7. And it's saying a particle of mass is projected from A with initial velocity perpendicular to OA and moves under central force along elliptic path, which is represented by R equals R sub theta over 2 minus cosine theta. R sub naught, divided by 2 minus cosine theta. Show F is inversely proportional to the square of the distance R from the particle to the center of the force. Using a certain equation. It does give you an equation that we have to play around with. Okay, so what do we got going on? What is this thing saying? Okay, it's saying we got a thing, central point O. We've got a particle here. The particle here is got a velocity in this direction. It's experiencing a force in this direction. And let's imagine it's travel, right? It was here earlier. It's going around. It's an elliptic orbit. That's V sub 0. And then we have a radius from here to here, and then we have our radius sub naught. So what's happening? Well, it's an elliptical orbit, so it's going to be going faster, speeding down, going faster, speeding down, depending on where its position is on that guy. So, cool. That sounds not fun. Okay. So, what do we have? We have R is equal to R naught, 2 minus cosine theta. And we have to show that F is inversely proportional to the square of the distance R. Okay, so that's essentially show that F is one of these guys to the square of the distance R from the particle to the center of force. And we have to use this equation to do it. Equal to 2 over r theta. Well, okay. I'm just looking at my notes here, trying to figure out the hell I did. Okay. Well, let's get to it. Now, one thing that's also given is U is equal to 1 over R. So, if we know that U equals 1R, and so in that case, we know that U is equal to 2 minus cosine theta over R sub naught, because place R to that. Okay. So now, what we are going to do is we're going to sub it in. So we're going to have, it's not a partial. Maybe it's a partial. I didn't check if it was a partial. U is equal to, we're going to take the differential of this. And what that is going to do, that is going to equal, we're going to pull out the 1 over r theta. So that is a partial. And we're going to have the derivative with respect to the angle, so d theta of 2 That goes away. And then we're going to have negative negative d theta. Let's go. Let me double think that. Okay, my notes are wrong. No, my notes are right. It's just my handwriting is terrible. I'm trying to figure out what the hell I did. Okay, so derivative of that 0, and derivative of this. So we're going to end up with du d theta is equal to 1 over RO, and derivative of cosine is going to be sine, and we are going to have a times negative sine theta. So that's essentially saying that du d theta is equal to negative sine theta r sub naught. Let's make sure that all seems kind of kosher. There's one of those times where it's like, I know the derivative of cosine, but now I'm wondering if I'm missing a negative. So I'm going to look it up real quick. I should know. I use it every day. Ahaha. That's a negative, so that turns that into a positive. So derivative of cosine is negative sine. We have negative here, negatives cancel. Sometimes you do something for so long and you start to doubt yourself. Okay, so now what we can do is we need to take the other derivative of this. So we have the derivative, first derivative. Now what we need is we need another derivative, the second derivative. d theta. Sine theta or theta. And that is simply going to be cosine theta over r sub naught. And that is going to be this guy. It's kind of bugging me. I don't remember how to call that operator, or how to call that the double integral. D squared theta, no, d squared u over d theta squared. Yeah, it doesn't matter. It's not important. It's not important. Okay, so we can go ahead and sub that in. So what we know that if we look at our equation, this 2 over r theta is equal to force over times height squared times, what is that, u squared? D squared. R squared, sorry. So we know that u squared is equal to 1 over r squared, which equals 1 over r squared. So we can sub that in. So let's do this over here. It's a little bit cleaner. We have 2 over r theta is equal to f over lambda h squared times r squared. Multiply both sides by r2, and that gives us it's going to give us 1 over r2 times 2 over r theta equal to f over m times h squared. Now, what we can do here is we're going to have f is equal to m times h squared times 2 over times r theta. And we know that that's a constant, that's a constant, that's a constant, that's a constant. So that means we're going to have a proportional to 1 over r squared. Now, before we get too ahead of ourselves, let's go ahead with the proof of how we know. How do we know that that equals 2 over r theta? Well, the way we know is we know this is cosine r theta, this term, plus 2 minus cosine theta. So, if we simplify that, we are going to have 2 minus cosine theta plus cosine theta over r theta. So let's go equals 2 over r theta. That's the proof for that guy. That's kind of a roundabout way of doing it. I don't know why I was thinking of doing it that roundabout way, but there you go. That's how I did it. That's how I did it. Okay. Problem number 8. Problem number 8 is saying that solid waste. I don't love the red, but it's fine. The satellite describes a circular orbit at an altitude of 19,110 kilometers above the surface of the Earth. Determine the increase in speed required at point 8 for the satellite to achieve the escape velocity and enter a parabolic orbit. B, the decrease in speed required at point A for satellite to enter an elliptic orbit at a minimum altitude of 6370 kilometers, and C, the eccentricity. So, A. We want the increase in speed rect to enter. Okay, so let's go with that version. So, what does that mean? Well, got a little Earth guy. If we go perfectly around it, we're in circular orbit, right? If we go like this, we're in a parabolic orbit, right? And at a certain point, like, let's go back to circular. If we go too far out, we escape. If we slow down, we drop back in. So, you know, that V escape minus V circ equals the difference in speed required. And this is going to be para slash hyper. So circular orbit goes around. We need the parabolic or the hyper velocity needed. The difference of that is how much you need to increase your speed to escape that orbit. Now we know that the escape is equal to our 2G m over r theta. That's for parabolic slash hyper. And V circ is equal to Gm over r theta. And that is for circular orbit. So let's figure out our escape velocity. The escape is equal to 2 times 6.67 e minus 11. And then units. And then 5.972 E24. And that is the mass of the sun, I believe. And our theta is going to be, let me double check. We're going to have $19,110 kilometers. That's how far we're orbiting above the Earth. But we are also our radius at, oh, yeah, okay. I was just checking my notes, and I was like, why did I put that in there? We need the radius of the Earth, because if we look at the problem diagram that I did not draw out, we have the Earth here. And the Earth has a certain radius, r. The Earth has a certain radius, r. And then we are here. So we are 19, 11, 10. The radius is 6370. So that is our total radius, or total radius, our true radius. That's the mass of the sun, or mass of the sun, that's the mass of the Earth. So the escape velocity gets you 5591 meters per second. But we need to figure out what it is for V circular. That is going to be equal to 2 times 6.67 e minus 11, 5.972 e24, and we don't need that. Ooh, that was close. 19. And that gives us 39.53 meters per second. So what we do is we take this term, we subtract this term, and then we have a difference. The delta V difference is actually 1638 meters per second. Cool. So that solves A. So that is how much you need to increase your velocity to escape the Earth's orbit. And you know, it's really similar to the problem with the rotating stage. You know, you have a tangential component of acceleration, and a normal component, and a total. And at a certain point, you exceed the force of friction, and then it'll just slide off. The force of friction in this term is the Earth's gravity. Okay, B is, let's write that up here. We have this answer. All right, B. B is asking the decrease in the speed required at A to enter elliptic orbit at a minimum altitude of 6370 kilometers. Okay. So that one is not too bad. We know that the circular velocity is higher than the elliptical velocity. So what we can do here is we can use our equation. We know that to find velocity at point A and velocity of B at point B, you know that angular momentum is conserved. That's what our H term is. So we need to find H. We need to find our angular momentum first. So what we can do, the way we set up our equation is we can have radius of A plus the radius at B, the radius of A times the radius of B. It almost looks like some sort of voltage divider problem, but it's not. So it's going to set up our equation here. We're going to solve for angular momentum there. And what we can then do is manipulate that RA, RB, RA plus RB to GM, and then solving for H gives us, let's just go for 8.21 E10 meters squared per second. Now what we know is with our angular momentum, we know that V is equal to that divided by the radius. So at point A in our diagram, we have 8.21 e to the 10, and our radius is going to be 2.55 e to the 7th. And that's given by the graph that we don't have here. Well, I have, you don't have. So that's a bummer. So that's going to be 3,222 meters per second. Now the point at B is again going to be our angular momentum divided by our radius, but we really don't need B. So we're not going to need that. So what we can do is to enter an orbit. We already have the A, and A is going to be, again, if you're here, this is A. We can figure out how fast we're going here, and we just figure out what we need to do to slow down. So we can just take that difference. So take the V circular minus VA. That's the point that it would have an elliptic orbit. And we can essentially do V circ minus VA, which we did earlier for V circ. That gives us 3953 minus 3222, and that is going to be 731 meters per second. Okay. solve for the eccentricity. Eccentricity E. So we know that the eccentricity is related to Ch2 GM. Now we already have that term. We're gonna have that term. We're gonna have that term when we solve for C. And we know that our C value is equal to RA minus RB over 2RA RB. So let's solve it. And in this particular problem, we have 255 E7 minus 127 E7, 1.27 E7, and 2 times 2.55 E7 minus 1.27 E7. C becomes 1.9 E minus 8. And then we put that there, put in our value for angular momentum, gravitational constant, and mass of the Earth, and our eccentricity of the ellipse. That guy. Great. You know, astrophysics is good. Astrophysics is actually not my favorite. I mean, it's okay. I don't prefer it. I really don't. So, meh. It's not my favorite. Last problem. We have to show that for satellite in elliptic orbit, curvature of orbit at each R0 and R1, the perigee and apogee can be denoted by 1 over, I don't remember how you call that in Greek. Greek? Rho. It's rho. Rho. 1 over rho is 1/2. And let's draw that. We'll draw that one because not having drawings sucks. It's really hard to understand, and it probably seems like I'm just doing equations, and that's a bummer. Let's do this. Oh yeah, look at that contrast. Now we're getting fancy. Okay. Now here we have r theta, and we have more 1. Okay. And we know that the relationship for that is RA plus RB over RA plus R times RB is equal to 2 times the gravitational constant times the angular momentum. Okay. So, divided by 2, and then we have 1/2 RA plus RB, RA, RB, gravitational constant times mass times angular momentum. And we also know from other equations that the force is equal to gravitational constant, mass of big one, mass of little one, and r squared. Mass of the big object, mass of the little object, and that is going to equal mass times acceleration, so we can get rid of that. So if we solve for acceleration, we know that the acceleration, the normal component of the acceleration, is going to be equal to gravitational constant to the mass of the big guy times radius squared. And we also know that the normal acceleration is actually that here. It's the velocity times rho, velocity squared over rho. And the other way of expressing expressing that is we know that is related to the angular momentum squared, or the radius squared rho. Now, if we sub this statement into this statement, we're going to have angular momentum over r squared rho equal to gravitational mass, the big guy, times r squared. And we're going to do times by r squared times by r squared. And we have now gone angular momentum over rho is equal to GM. Jim's making a comeback. Okay. So rearranged for this, if we divide by angular momentum, we're going to have 1 over rho is equal to GM over angular momentum, which, what would you know? Look at that. That's our term right there. That's that guy. All right, so we can sub in, and we're going to go 1 over 2, 1 half. All right, RB is equal to 1 over rho. And where we can separate this out, if you were really anal about it, is, separate that out, RA over RA, RB. RA's cancel out, we have 1 over RB. Separate RB, that cancels out, we have 1 over RA, which is the same as we have here. So that is how you show that the satellite elliptic orbit can be denoted by that equation. And apogee, the furthest point, and apogee, the closest point. That was a fun one. Thanks for watching.